Hey, excuse me. Hey guys, we're going to talk today about, in chapter 15, we're looking at 15:1 through I think 15:5. And as we look here in chapter 15, what we're going to be talking a lot about is the first and second law of thermodynamics. The first law, okay, of thermodynamics, make that look like a W, of thermodynamics. Oh man, my handwriting is terrible today. Thermodynamics. Ooh, that's a big word. First law of thermodynamics boils down to this. Every substance or mass or matter has a certain amount of internal energy. We often indicate that by the temperature. Now, energy and temperature are not the same thing. Okay, temperature is a measurement of the average kinetic energy of a particle. It has to do with that more than it does to do with the actual energy that's inside of a substance. But they're directly linked in that the more temperature something has, the hotter the temperature, the more internal energy there will be inside of that substance. And the idea of the first law of thermodynamics is that if there is a change in the internal energy of the system, that's this U, internal energy, then that change will come about because either heat was added, so there's our Q. If we add heat, energy, which is transferred by the fact that there's a difference in temperature, so we're changing the temperature, we're adding heat to it because of a temperature difference, minus any work that's being done by the system. So if you think about a gas inside of a piston, we can ignite that gas and add heat energy to it. But if that piston is then driving something, that gas as it explodes pushes on something, does some work, the actual change in the internal energy of that gas might not be as much as you'd think it would be. So there can be work done by the substance or by the system as opposed to heat energy being put into the system. At the end of the day, these are all measurements of energy, so they're all measured in joules. And depending on the type of reaction or interaction that we're experiencing, we will have different of these values being held constant in each of those cases. So for instance, there's three big ones that we're going to talk about. There is a fourth one, but the three that we're really going to talk a lot about are the isos. So we have isothermic. If we have an isothermic transformation, that's supposed to be MIC, isothermic, that would mean that the change in temperature was zero. There's no change in temperature, which implies that the internal energy of the substance did not change, which would mean that the heat that's added to the system is equal to the work done by the system. So I'm adding this heat energy, but it's doing work, and at the end of the day, there's no changes in temperature. We're going to talk a lot about a PV diagram where we measure pressure against volume. An isothermic change will create a 1 over x curve. If you think about the graph 1 over x, that's how it's changed. It's a direct invert. It's an inverse variation, but that would be the change, whether I'm going to high pressure, if I go left, or I go to low pressure as I go to the right, as I go to the right, it's going to follow this curve somehow. This would be an isothermic curve. The next one is adiabatic, which is actually just a steeper version of this. It actually drops down a lot faster. But we're not going to do that one. We're not really going to focus much on it. We are going to talk about isobaric. And isobaric means that the change in pressure is equal to zero. Okay. And so what that looks like on a PV diagram, if the pressure is held constant, that means it would be a flat line across. So a graph like that would be isobaric. And the last one of these graphs that we're going to talk about, isovolumetric, which means delta P equals 0. As a delta V, sorry. As a byproduct of delta V being 0, we actually find out that the work would be 0, which means that the change in internal energy would be equal to any heat added to the system. So you add heat to it because we're allowing the volume to be held constant. No work is being done, no actual. If you think about volume and a piston being held constant, that means the piston didn't go up or down, which means nothing moved. And if you think of work as force times displacement, if nothing's displaced, there couldn't have been work done. And so this last PV diagram, if the volume is held constant, would be a vertical line. Whoops, that's not a very good example. But imagine that it's straight up and down, would be isovolumetric. You're going to draw a few PV diagrams. It's going to tell you, hey, stage 1, this happened, stage 2, this happened. And just use these 3 different shapes of curves to try and get from point A to point C, or back to the beginning if that's where they want you to get to. At the end of the day, we're really headed towards this concept of a heat engine. And a heat engine, you guys, you do know what they are. You've got them in your life, or you're in the world you live in. You might not always think of them as quote-unquote heat engines, but I want to make some good examples. If we talk about a steam engine or a steam turbine, anything like that is a great example of a heat engine, where we're using a temperature difference to drive a turbine or a motor. So if you can imagine with me in our heat engine that we're going to model down here, okay? Imagine that over here, we're going to call this QH. We've got a high temperature or high heat reservoir. You could think of it as a bunch of water over a flame, okay? And it's going to make this go up into steam, right? So we're going to boil this water. This is essentially a steam engine. As that gas gets hot, it's going to expand and it's going to put pressure everywhere trying to get out. Now, if the whole environment that it's in is also extremely hot, then it's going to be at an equilibrium and it's not going to try to move. But if I create a little hole over here, a little pipe, if you will, okay, and I, on the other end, have an exhaust, we'll call it QL, a reservoir of cool air, okay, a place where it can cool off, or where all that heat could go and level out, be equal with the universe. This hot air is going to want to go down this channel. Okay, it's going to want to go towards that. Now, if along the way, okay, I put a little turbine in here, and that air comes through and it pushes the turbine and makes it spin as it goes down into the cool reservoir to cool off, I'm going to get some work out of this, aren't I? Some of the energy from that hot reservoir is going to get spent pushing that turbine around as it tries to find its way to a cooler environment. So that work, okay, is going to be a portion of QH. Now what's really cool is when we take this QL and we allow it to flow back into our reservoir. Then we have a cyclical or a cycle that we can repeat over and over again. And this is how most of our steam engines and internal combustion engines, things like that, they work. We allow more oxygen air intake into the reservoir, and we exhaust into the environment. Anyway, very similar to this happens with a lot of turbines and steam turbines. We use them coal-fired power plants. All they do is boil water. Just like nuclear power plants, their goal is to boil water. And that's how we produce our electricity. So this is an example of a heat engine. At the end of the day, we end up with this assumption that QH will equal QL plus any work done as a part of the system. And if we want to know how efficient a heat engine is, the efficiency of a heat engine is the amount of work done compared to the amount of energy you had to start with. Did you get 60% of the energy to do work, or was it only 20%? Knowing how efficient something is allows us to know just how good we're doing. Now that being said, if this QL was really low, then when I bring it back, it would take a lot of energy to heat it back up. So the fact that I'm not getting all of the energy out on the first pass is okay if I can cycle back through and start maybe in a better position. We're never going to be perfectly efficient. But there was a French scientist by the name of, I'm going to mess up his first name. Sadi Carnot. Okay, Carnot. It's an O. Carnot, who wanted to understand and predict how perfect could we get a heat engine to be? Is there a way to get it to maximum efficiency? And he developed what's called a Carnot engine. It was a theoretical engine, doesn't exist, but he wanted to get it to its best case scenario. And what he found was that there was a relationship to the, let me erase that, that was wrong. Let's go back up here. There was a relationship between efficiency and temperature that he could exploit in this way. And so he said that the ideal efficiency, ideal efficiency of any heat engine would be the work done divided by the heat added, or the original amount of heat. Well, he can't do that in terms of the work. There was an issue there with that calculation there, but if we change the work and the heat into temperatures, then the high temperature minus the low temperature divided by the high temperature would give us this ideal efficiency. Now notice, the bigger the difference between TH and TL, if that's a big difference, then when I divide it by TH, I'm going to get more and more efficiency. Think of it this way. Let's say, and these have to be in Kelvin, let's say I had a temperature difference of 100 Kelvin as compared to 250 Kelvin. All right, let's take that comparison. The difference would be 150, and let's be divided by the high temperature of 250. So in this case, if those are the running temperatures, right, my engine is running at 250 on the inside and 150 is the exhaust. If that's the differences there, then 150 divided by 250, I should know this one, it's 60%. I get a 60% efficient engine. However, if I can just widen the gap, right? Let's say that I keep the exhaust at 100 Kelvin. That's really cold anyway. But let's say I get this up to 350. Okay? Well, the difference now is not 150, it's now 250. But I am dividing by a bigger number, so does that matter? It does, but it doesn't matter as much as the fact that we have a bigger gap. So there I'd have a 71% efficient engine, okay, and so on down the line. Now, the idea is, like, how do I ever get this to be perfect? What would I have to do to get 100% efficiency? Well, the only way this equation would ever equal 1 is if TL equals 0. Because look, then I'd have TH over TH. The only way that happens is if the exhaust temperature is at absolute 0. That is not just practically impossible, it's theoretically impossible to get down to where there is no heat internally in the substance at all. It's not going to happen. So we know we can't have a perfectly efficient engine, but just how good can we get? And when we look at the actual efficiency of some engines compared to their ideal efficiency, we can recognize pretty quick we're not getting a lot out of them. You know, a 40% efficient engine is pretty dang good. So anytime we can find ways to increase efficiency, it's going to make a long-term impact in the environment and the world that we live in. So hopefully this has helped. Second law of thermodynamics. Shoot, I went right past it, didn't even think about it. Has everything to do with this heat engine. Temperature, or heat, rather, heat will never flow from a cold reservoir to a hot reservoir on its own. If you think about grabbing a cold rock outside, or a snowball, heat will leave your hand and go into the ice. You can't spontaneously expect that the warmth, there is heat inside of the ice of the snow, but it's just so low that you wouldn't ever expect or think that that temperature, that warmth that does exist inside of the ice would leave that ice to come into your warm hand. It's always the opposite. We let heat vacate a warm substance into a cooler substance. That's the second law of thermodynamics. If we want it to go backwards, like in air conditioning, well, then we're going to have to do some work to make that happen. And that's something we're going to pick up next time we meet. Good luck.